Okay, everyone. So we're going to get started today. Thanks for attending the session. My name is Angela Chin. I'm a software engineer at Pivotal, and with me is Usha Ramachandran, who's a product manager at Pivotal. A little bit of background: why are we wearing these hats? Why are we giving this talk? So we're both have worked on the networking team for Cloud Foundry, which is a platform as a service. On the networking team, we've really been focused on, of course, container connectivity and communication between containers running in Cloud Foundry. And so as part of the journey of working on the networking team, we decided to build our own CNI plugin, hence the Silk Road, building a CNI plugin from scratch. So we'll just do a brief overview of what we're going to talk about here today. The first thing is just to make sure that we level set on what is CNI. It's a very high-level overview, just make sure we're all on the same page before delving into what is Cloud Foundry, again, to understand why we built our own CNI plugin. We'll look at CNI plus Cloud Foundry before talking about the main motivations behind why we decided to build Silk, before talking about the design decisions that we made at a high level in order to meet the requirements that we were looking to enable. We'll look at what's next for the future of our networking plugin before finishing off with some key takeaways. So we'll start with what is CNI. So CNI stands for the Container Networking Interface, right? And it's an industry standard API for container runtimes to call out to networking plugins. And this is sort of just the bare definition. So why exactly do we have CNI, right? Like, why do we create it? Why is it part of the CNCF? Like, why do people care so much? And it's really because you're going to have different use cases. You're going to need different capabilities for your networking stack, depending on what hardware you're running on, what your use cases are. And so instead of having your container runtime also deal with setting up the networking stack for your container, you want to be able to have it pluggable. You want to be able to choose your own solution, maybe add additional features. And so CNI really allows for that extensibility. So for the purpose of this talk, we'll be focusing on CNI plugins. So what actually implements your networking interface, what sets up the networking stack for your container. So the container networking interface, right, is an API. It's a specification. And what it deals with for CNI plugins is two main things. One, it deals with creating the network interface for containers. So again, analogous to in the CNI specification, CNI add. And it also deals with removing these resources when you delete a container. So making sure you clean up after yourself. It's also important to note that delete is idempotent. So this means that you could get into a partially torn down state. You can run delete many times. Maybe you actually did clean up. It should never fail. And at its core, CNI plugins deal with network connectivity. So we're really looking at making sure that our containers are able to be reached, that we can send, receive packets. You can do all kinds of fancy things with CNI plugins. You can do things like traffic shaping. You can do things like host port mappings. But at its core, CNI is really about the network connectivity aspect of it. So CNI plugins normally come in the form of binaries, right, that you run. And they are invoked during a container create and delete, obviously, because you're doing the addition and deletion of your networking stack. And arguments, just at a high level, very quickly, for CNI is passed in through a mixture of environment variables and standard in the form of a JSON format to say how exactly you want to set up your networking interface. And again, this is all documented in the CNI spec. So we talked about how we have the use case for CNI because we want to bring many different solutions. So here's just a list of many different CNI plugins that are out there. As you can see, it's extensive. But for the purpose of today's talk, we're really going to focus in on Silk, which is, if this ever moves, no, can you hit next? I think this died. Is a CNI plugin that's designed for Cloud Foundry. And so to understand our journey, to understand why we decided to build Silk, we need to look at Cloud Foundry first because we designed it for this use case. And so I'll hand it over to Usha.
Thank you, Angela. All right. Looks like this clicker may be a little temperamental, but we'll work with it. So I'm going to spend the next few minutes just introducing Cloud Foundry. There's a lot about Cloud Foundry. In fact, there's a whole conference dedicated to it. So I'm going to try my best to just give you a quick overview of what the platform is and what are some of the networking-related aspects of it that affect what we did with our CNI plugin building. Just a quick show of hands. How many of you here are familiar with Cloud Foundry? Okay. Looks like maybe about half the room. All right. So just to get started, Cloud Foundry is, there's a simple haiku that basically describes some of the principles of Cloud Foundry, and it's coined by Onzi Fakuri from Pivotal. And it basically says that here is my source code, run it on the cloud for me, I do not care how. And this principle kind of forms the basis for a lot of the activities or the features that Cloud Foundry supports. So at its core, Cloud Foundry application runtime is your building block that's going to run and manage your applications. So the idea is that as an app developer, you can concentrate on writing code, and everything around the life cycle of the application, such as patching it, scaling it, routing to it, applying security policies, all of that is taken care of by the platform. And it runs on a infrastructure layer called BOSH that manages your infrastructure, and it's responsible for the lifecycle management of the components that are going to host all your applications, as well as the control plane for it. So both of these platforms put some specific requirements on building a CNI plugin for this platform. So just to give you a quick idea of what happens so that maybe you can draw a parallel between, say, a Kubernetes lifecycle and a Cloud Foundry application lifecycle, is that as an app developer will push code using a very simple command called cfpush. It includes usually an app manifest that has properties that describe the application. And the next step is this will go to the Cloud Foundry API, at which point it'll go to a container orchestrator, which will then schedule it to one of the hosts that are going to host the containers. We call these hosts cells. There is a container runtime that is responsible for the life cycle of the container on the host while it exists. Typically in Cloud Foundry, the container runtime was responsible for the networking for all the containers. It's also responsible for setting up file systems, etc. With CNI, we actually extract out some of the networking functionalities. The last part for an application is to register a route so that it's accessible from clients that are trying to connect to it from outside. And the component that does that is a co-router. So in terms of networking, there are a few things that applications on Cloud Foundry have to deal with. One is, of course, being available from the outside to connect in, and then connecting from an application to a service that's sitting outside the platform. The typical way for applications on the platform to communicate outside is through the use of NAT. And we have egress security firewall rules that can control that traffic through a feature called application security groups. So that's a very, very high-level view of the life cycle of an app within Cloud Foundry. So let's talk a little bit about where Cloud Foundry and CNI intersect. And to do that, we have to take a couple of steps back to just understand how legacy Cloud Foundry networking worked. So as I mentioned before, the way application traffic goes out on Cloud Foundry today is that everything is natted out. And so that meant that the app identity is basically lost. If you wanted to do direct container-to-container communication, you had no way of doing that in the traditional stack. And this made it difficult because there are some inefficiencies of always hairpinning through the ingress gateway. And also in terms of applying policy, it's difficult to do that if you don't actually have app identity. So our ideal state was basically to have a direct connection between containers so that you had containers that were identifiable, you could apply policy between them, and you could have more efficient traffic paths within Cloud Foundry. So I'm a PM. I love, coming up with requirements. So in terms of requirements from the networking stack, the first thing was, of course, that the legacy features for Cloud Foundry continued to work. So we wanted to provide backwards compatibility. And so what that meant was that the existing NAT-based workflows would continue to work. Application security groups continue to work. The second part is connectivity. As I mentioned before, we wanted to provide every container with its own IP address, and we also wanted to be IaaS agnostic, because the way Cloud Foundry works is that you can deploy it on any cloud. So we really wanted this container addressing to be, to work across any different cloud. And finally, we wanted it to be extensible. Mostly because there are other solutions. Angela showed a whole bunch of CNI plugins that are available, as well as SDN solutions that you might want to deploy. And so extensibility was another big requirement in terms of connectivity. Okay, and the last part, was policy. So policy is basically allowing specific applications to talk to each other, having it dynamic as well as being self-service. Since we're talking about CNI, we're going to focus this talk on the connectivity aspect of our requirements. And the main things we wanted for connectivity was that it was IaaS agnostic, that there was a unique IP per container, and that it was extensible. And so what this turned out to in terms of a solution was actually to use a VXLAN-based overlay so that it would work in any environment, and to allocate a subnet per cell from which every single container could get an IP address. And then finally, to leverage CNI so that it could be extensible and you can replace the batteries included CNI plugin with anything that you choose. So maybe you are thinking that this sounds a lot like flannel. And you're right. So we started off with actually implementing flannel as a solution. And along the way, we found out that we had some motivations for building our own CNI plugin. So I'm going to talk a little bit about what led us down the road to Silk. So I'm going to walk through some workflows, like kind of slowly, and then in your mind you can imagine that this is happening across the board for like thousands of application instances, and in a system where things are changing all the time. So the first thing is that application containers can be added or deleted at any time. So you can delete containers, add new containers, scale up containers. The second thing is that your Diego cells that are running the containers themselves can be destroyed and recreated. And this is done by Bosch without any operator involvement. So when that happens, all your containers running on a cell are rescheduled to another cell. They're evacuated. And your once you clear out all the containers, the cell is deleted. And similarly, you can, okay, all right, the cell is gone. The cell came back. So similarly, once the cell comes back, you're going to have to reschedule containers back on it. And here again, there is some, just in terms of the life cycle, when can you start scheduling containers to a cell? What if I schedule a container when the networking is not yet ready to set things up? So these were some of the things that we ran into and had to find out solutions for. The other thing is, how do you keep your networking running when you have network partitions, if you're storing state somewhere outside, how do you deal with actually losing all your networking state, right? How do you recover the system? So a lot of these requirements ended up around just making the system available and reliable across many different lifecycle events. So that was the primary motivation for trying to build our own plugin, which was to make sure that networking was stable across many different lifecycle events. A secondary consideration was also extensibility. So starting from an app-to-app policy, we wanted to extend security to also include things like services or the Go router. And in order to do that, we'd like our CNI plugin to start supporting other types of entities, not just app containers. So now that you know the why behind why we wanted to build Silk, I'm going to hand it back to Angela to walk you through how exactly we did it.
Great. Thanks, Usha. So we'll just start again with a high-level overview. So Silk, again, is a CNI plugin that we built. At its core, it allocates a unique IP per container, and it does its networking using a VXLAN overlay network. And so Silk is composed of three main components that we can see here in red. We have the Silk controller, we have the Silk daemon, and we have the Silk CNI plugin. So the Silk controller is the control plane component, not very great at naming, that deals with being given an overlay network, allocating and distributing that overlay network, splitting it up into subnets and giving the subnets to each host that wants it. The Silk daemon is a local process running on each host machine. It deals with first acquiring the subnet from the Silk controller, renewing the lease it has on that subnet from the Silk controller, and also deals with setting up all of the routing for the state of the world. And lastly, we have the Silk CNI plugin, which is the binary that's called during the container creation and deletion, which sets up your network interface and also allocates the unique IP per container. So when we decided to build Silk, we had several design considerations in mind. First and foremost, reliability and stability. So just to make sure that we're all on the same page again, we made several decisions around a concept in Silk known as a lease. A lease is basically a subnet given to a host VM. So the Silk daemon will ask for a lease. The lease is the subnet from which it can allocate container IPs from. And so the first design consideration we decided to do around leases was that a lease is given only if there are no containers on the cell. And the reason we did this is because you can imagine a use case where you have containers on the cell that have some container IP, and Silk daemon needs to acquire a brand new lease for some reason or another. Maybe there was a network partition and it comes back up and the lease it had before, the subnet it had before, it can no longer acquire. So it asks the Silk controller for a new subnet lease. Well, then you're going to have a mismatch where the host thinks that it can allocate subnets from a specific, or allocate IPs from a specific subnet, but there are containers still running on the cell that don't fall within this range anymore. And then you're going to have a loss of connectivity for these containers. And so the first thing that we decided was that you can't acquire a new lease unless there are no containers running. You can renew leases, but you can't acquire a new one. The second design decision we made was that the network ad would fail if the daemon didn't have a lease, which seems pretty straightforward, right? If you don't have a lease, if you don't have a subnet, what are you allocating container IPs from in the first place? And lastly, the final design decision we made was that the lease should be kept for as long as possible. And this was truly to prevent against the case of long-lived network partitions. Because let's consider that a host VM is partitioned from the control plane for a long period of time. The best case scenario would be when the partition is fixed, that the host, the Silk daemon running on the host, would be able to renew the same lease because it has containers running on it, so it can't get a brand new lease, and the containers would be connected again. So we wanted to make sure that we were protecting leases. We have an idea of lease staleness, where a lease can be stale, but we won't allocate it out to another host until we've run out of leases that have never been allocated before. So how does this all fit together? Let's consider the case of a subnet assignment. We have a new host coming up for the first time, and we have the Silk daemon running. The Silk daemon will reach out to the Silk controller to ask for a subnet lease. Because it has no containers running on it, it happily is given a subnet range from which to allocate IPs from, so that when a developer decides that they want to create containers, they're able to have their container runtime initialize the process of creating the container before calling out using a CNI client library over the CNI API to the Silk CNI plugin. The Silk CNI plugin will create the network interface and will ask the Silk daemon what subnet range it can allocate a container IP from. Choose a container IP, and then the container creation can be completed. And of course, this can happen for multiple containers on a given host machine. Now let's consider the case where you decide to restart your host. Maybe you're upgrading. And so in this scenario, the first thing that happens when you decide to do a restart is you need to evacuate all of the containers off, schedule the workloads elsewhere. Then, when it comes back up, the Silk daemon will once again need to acquire a new lease. Because this host machine has been around before, it's not brand new, it has an idea of what lease it had in the past, and so it will initially ask for that same lease. If that lease wasn't available, it could acquire a different lease because there are no containers running on the cell. But in this case, let's say that it's able to acquire the same lease, happily does so, and again, is able to successfully create containers on the given host. So those are some of the design considerations that we made around reliability and stability. Let's also talk about the actual architecture of the network that Silk creates. I guess after this, I totally forgot. The final thing that we did in terms of reliability and stability was to add the ability to call a teardown from the Silk binary. And the reason we decided to add an ability for a teardown, again, goes back to the fact that we knew how we were going to orchestrate our control plane, how we were going to orchestrate our container creation. We knew we had a certain lifecycle management process, and so we are able to add this ability to call teardown so that whenever a new cell or a new host was restarted, the first thing that we would do is call this teardown to make sure if there was any leftover networking state, that would be wiped away clean. So these are design considerations where if you're designing for a specific use case, you can really take advantage of knowledge of how your runtime system works and knowledge of how you orchestrate it to make sure that you're adding some of these benefits. And with that, we'll get to the network setup. So as Usha mentioned before, one of our main goals was that our network setup had to be IaaS agnostic. And so we decided to use an overlay network with VXLAN. How does this look? Let's consider the use case of having two applications on two different hosts. And for the sake of switching things up, let's say app B actually wants to talk to app A this time instead of the other way around. In this case, we see that we initially send out this container to container packet with the source and destination IPs being the source and destination IPs of the host, or of the source and destination container IPs. In this case, we actually then have this packet virtually routed to the Silk VXLAN, where it's encapsulated in an underlay packet with the source and destination being the source and destination IPs of the host machines. It will then be correctly routed through a switch to the destination host, where it's de-encapsulated and then correctly virtually routed to the destination and forwarded along. Note here that this is a distinction from Flannel, which deals with a bridge. Here we don't have a bridge. We deal with everything in a sort of, or through virtual routing. And so from the container's perspective, it's a single flat layer 3 network. And this protects against things like broadcast storms and ARP spoofing. So that was some of the considerations. There were many more that we've made, far too many to go into today, when building Silk. But you might be wondering, did you just build a CNI plugin and leave it alone? What's next, right? What are you actively working on? So I think I can't walk too far away from this. What's next? So the first thing that's next is CNI chaining, which is really hot, really cool. It's the ability to chain your plugins. So before, in the previous state of the world, with our setup, which is still the current state of the world, I guess, we would have the Garden External Networker, which is our CNI client library, call out over the CNI API to the CF Wrapper CNI plugin that we maintain. And this deals with the legacy state of Cloud Foundry that Usha mentioned previously. And then the CF Wrapper CNI plugin then had to delegate out to Silk. So we were nesting plugins in this scenario. But with CNI Chaining, you now have the ability so that your CNI client library can call out again to the CF Wrapper CNI plugin and then to Silk CNI plugin, but have that result returned back and use that result that's returned to call out to some other CNI plugin. We're even envisioning a world, although this definitely is not set in stone, where we no longer have to do the nesting. So we can call to the CF Wrapper CNI plugin, have the result returned, and then chain out to the Silk CNI plugin, or vice versa. So chaining has been a really popular topic. It's really great for additional features that aren't part of the core network connectivity aspect. So maybe you have your first plugin that sets up the networking interface and you want to do some additional feature to it. One such use case that we actually had in Silk was the ability to do bandwidth limiting. And so we actually extracted out that code and contributed it back upstream to the CNI community in the form of a bandwidth limiting plugin. So this is now accessible for everyone to use. It's in the CNI plugins repo. And it's actually being currently merged into Kubernetes as well for use. And so we're looking to also extract that code out from the Silk CNI plugin and do plugin chaining with the bandwidth CNI plugin that we've recently added. The second thing we're looking at for the future of Silk is, if I can go, is having it used by other container runtimes. So at its core, we said Silk is a CNI plugin designed for the Cloud Foundry use case, and this is true. But we think that it could be useful for other container runtimes as well. We've done work in the past to see that it runs as a CNI plugin for Kubernetes, but there's still some work to be done before it would be something we'd consider production ready. So this is on our radar as well. These are just a couple of things that we're looking at for the future of Silk, but with that, I'll let Usha take it off with key takeaways.
Thanks, Angela. So in terms of the key takeaways, what we covered here today was basically just an overview of CNI and how we used it with Cloud Foundry. What we found using CNI is that it's a really wonderful and simple interface to provide networking capabilities and extensibility for your platform. We certainly don't recommend that everyone go build your own CNI plugin. Look at the CNI plugin repo. There are a lot of options available, but there might be cases where you would have to build your own CNI plugin to get some capability that you need for a specific environment, such as Cloud Foundry. We also covered what Silk does and some of the unique characteristics of it in terms of better lifecycle management around when containers come and go and your host VMs come and go. And finally, we spoke about the bandwidth limiting plugin and CNI plugin chaining, new capabilities in CNI that we're starting to leverage, and we'll continue to contribute back to the community. So definitely CNI is really awesome. Try it. It's actually not that difficult. I was in a talk earlier today on CNI on creating small plugins to do additional things than setting up network connectivity. So with that, we thank you all for attending. Are there any questions? Awesome. Thank you.